Good morning, folks. All right, give me just 1 second to get the dot camera fired up and we will get started. Today we are going to continue talking about limits at infinity and section 2.6. And I think at the end of class today, I don't think it will take the full class time to finish the 2.6 material. So at the end of class, I'm going to start introducing the material that originally designated for this week, which is the introduction of the derivative, which is a really big idea. It's kind of the main idea in Calc 1, if I'm honest. I'm very excited to be approaching that, but I don't want to rush us there. I want to make sure that you're comfortable with all the stuff that we've been talking about regarding limits. So we're going to start there. I think QCam is playing nice. Yeah, I don't have to refresh this, so I can just connect the camera, share the screen, and we should be in business. Come on. There you go. There you go. All right. So today we're going to continue, or finish, I guess. Introduce. These are the two big topics for today. I'd like to show you a handful of more examples from section 2.6. Some of the examples we looked at last time were a little bit challenging, but we definitely did not cover the full array of different challenging and fun things that can happen when you play around with limits at plus and minus infinity. And then before we talk about the derivative proper, although we will have the tools, namely limits, in order to define it, I want to spend a little bit of time talking about rates of change and make sure that we're genuinely comfortable with the concepts that the derivative is meant to extend, because the derivative extends a concept that you're familiar with from your algebra classes. I think last time we left off with a limit at plus infinity of a function that I told you I was going to examine at minus infinity also. Well, I remember, I think it was the square root of 2x squared plus 1 all over x. I'd like to come back and make sure that I'm not misremembering that. Treat that limit with the care it deserves. But not here. What it was. Not crazy. Not crazy. Precise definition. Oh no, there it is. Okay, yeah. Okay, so last time we finished by showing, and it was an example, the limit as x goes to positive infinity of the square root of 2x squared plus 1 over x was equal to the square root of 2. it's been a couple of days, and the trick we used for this was a little bit weird. So I forgive you if you don't necessarily remember the trick, but what we did, the trick, was to divide top and bottom by x. In the top, we used x equals the square root of x squared. So in the bottom, I divided top and bottom by x, and then in the top, when I divided by x, I rewrote the x as the square root of x squared so that I could combine it with the square root symbol here. And that's what allowed me to combine all of my like terms and kind of cancel out the highest order term from the top and the bottom in order to get the value of the limit out. So remember, the game is to divide top and bottom by the dominant term, whatever the dominant term is. Downstairs, the dominant term is clearly x because there's nothing other than x there. There's no other contender for the dominant term. Upstairs, you do have an x squared, but he kind of lives underneath this square root. And since there's no algebraic way to simplify that square root, like I can't give it to those two terms separately because square roots fucking hate addition. The only way to get around it was to divide top and bottom by x, and then to insert that x when I tried to divide in the top as the square root of x squared. Well, there's something a little bit wrong about that. I lied to you a little bit. When saying that the square root of x squared is equal to x. Can anybody tell me what's the fib? What's wrong with saying the square root of x squared is equal to x?
X is 2 over 2.
I think I understand what you're saying there. So the power here would be 2 over 2, right? Because it's x squared raised to 1/2. And 2 over 2 is 1. So actually the arithmetic that's behind the algebra suggests that this is true. But there's something subtle going on here. Yeah, what happens if you plug -1 in here? Well, then you get the square root of -1 squared. -1 squared is 1, and the square root of 1 is +1. So if you plug -1 into this expression, you get the statement 1 equals -1. In fact, the square root of x squared is really the absolute value of x. Now, in the limit we were looking at the end of class last time, this guy, I was sending x to +infinity. So I'm imagining plugging in very, very, very big numbers for x. In particular, I'm imagining plugging in positive numbers for x. So this replacement didn't hurt us. Because if x is positive, then the absolute value of x is just x, and this is a true statement. However, the next example I want to look at is the limit as x goes to -infinity of this same function, the square root of 2x squared plus 1 over x. And the trick is going to be the same. I want to divide top and bottom by whatever the dominant term is. The dominant term downstairs is still x. The dominant term upstairs is still the x squared, but it's under a square root, so I can think of the dominant term upstairs as also being x. But now when I go to divide top and bottom, I need to be a little bit more careful because since I'm sending x to -infinity, I'm imagining plugging in very, very large negative numbers. So this discrepancy between the absolute value of x and x itself is going to be relevant. So I'm going to divide top and bottom what's the right way to say this? Yeah, divide top and bottom by x. Remember, x is negative, so yeah. I'm going to divide top and bottom by this by x in the same sort of way, but I'm going to do it carefully this time. So what I'll get here is the limit as x goes to negative infinity. My numerator and my denominator will look like this, right? So here I'm writing the bottom the same way I wrote the top last time. Last time I just divided by x, top and bottom. This time, really what I'm doing is dividing top and bottom by the absolute value of x. What you'll see is that the impact here isn't hard to understand or hard to work with, but the notation might be a little bit surprising. So I want you to just very carefully follow what I'm writing down, and then we'll talk about it. So take your time, carefully write down what I'm writing down. Downstairs here, this guy, I don't need the square root there. I really only need the square root upstairs. So I'll treat this as x over the square root of x squared, because that's what it is, right? The square root of 1 is 1. And upstairs here I'll merge the two square roots, and I'll have 2x squared plus 1 times 1 over x squared. So first I want to make sure, is everybody following the algebra so far? Dividing by the square root of x squared is very similar to saying I'm going to divide by x. That's what we did here. Upstairs, when I divided by x, I called it the square root of x squared. Here, I'm thinking the same way. I'm going to need to divide top and bottom by x, or something that grows as fast as x. And upstairs, I need to write that as the square root of x squared so that I can merge the two square roots, because my challenge is getting this thing to play nice. The challenge is coming from the square root. So upstairs, I do the same thing that I did at the end of class on Wednesday. And this time, instead of just leaving the downstairs as x divided by x, I'm going to treat it exactly the same way as I treat the numerator. Passing from here to here, the square root of 1 is 1. So this piece is really the same as, and there's no funny business here. This piece is really the same as that. And so when I multiply these two things downstairs, I'll get x times 1 over the square root of x squared. I'm going to adjust the paper a little bit. I'll keep this here. Okay. So here's the original problem. Here's our first step. Here's our second step. And down here will be our third step. I'm going to distribute the 1 over x squared underneath the square root upstairs. And I'll have 2x squared times 1 over x squared. Well, that's 2. Plus 1 times 1 over x squared. Well, that's 1 over x squared. Downstairs, x over the square root of x squared is x over the absolute value of x. All right, and just maybe to keep things clean, in case you have a hard time with the fractions, you might want to write little parentheses around the bottom because it is kind of a fraction within a fraction. We don't have obvious grouping symbols there like the square root. Here's where we need to pause and make an observation. So again, I want to make sure everybody's comfy with the algebra so far, because the algebra is kind of the main challenge here. Are there any questions about how we passed from here to here or from here to here algebraically? In other words,
I have a question.
Yeah. Yes, please.
How did it, so it's a law that the square root of x to the power of 2 is an absolute value, and when we're solving the problem, that's what you want us to write, the absolute value of x as we're solving?
So what I would like you to write as steps for solving the problem are the things that I just identified as steps. Like, we write down the problem, and then my first step would be just this, my second step would be just this, and then my third step would be this. It is a law that the square root of x squared is the absolute value of x. That is true. The reason we need to be careful about it here is because the x's that I'm imagining plugging in are negative. And so the trick that I used last time doesn't work quite exactly the same way as it worked last time. Because the same sort of thing that I talked about when we came back here, and I said, well, this isn't really true. Like, what happens if you plug in x equals -1, you get a false statement. Here, I am imagining plugging in very large negative numbers because I'm sending x to -infinity. So I need to be just a little bit more careful about what the square root of x squared really is. That's all.
But the steps are pretty much the same, right?
The steps are very, very similar, right? The only difference, so compare this. If you have your notes from last time, compare this. The step from here to here, the only difference is instead of writing 1 over x downstairs, I'm writing the square root of 1 over x squared, which is very, very similar to 1 over x. In fact, it's really 1 over the absolute value of x. So that's the only difference between the steps here and the steps in the last example.
Thank you.
Now, the funny business, or not the funny business, but the thing which will make the answer different here than it was when we took the limit as x goes to +infinity is this little thing downstairs. Has anybody ever seen the graph of the function x over the absolute value of x? Does anybody know the name of this function? Some pre-calc classes talk about this, some don't.
No, sir, I don't think so.
So this function has a special name. It's called the signum function, or sometimes just called the sine of x. Look at that. You guys seeing this? So if I plug in x equals 1, it spits out 1. If I plug in x equals 2, it spits out 1. If I plug in x equals 3, it spits out 1. If I plug in x equals any positive number, x over the absolute value of x spits out the number 1. If I plug in any negative number, x over the absolute value of x spits out -1. The denominator here returns the sine of x. So if x is positive, the downstairs here is +1. If x is negative, the downstairs here is -1. Since we are sending x to -infinity, the x's in this expression are less than 0. Therefore, x over the absolute value of x is equal to -1. All right, so x over x on its own, those cancel and you just get 1. That's what we saw as we worked on this example last time. The denominator just became 1. Here, the denominator becomes x over the absolute value of x, which is +1 if x is positive and -1 if x is negative, right? Because x over abs x equals 1 if x is greater than 0 and -1 if x is less than 0. Okay, so what that means is that the limit as x goes to -infinity of this expression is the same as the limit as x goes to -infinity of square root of 2 plus 1 over x squared, all divided by -1. This takes a little bit of thinking. I remember the first time I saw this being like, what the fuck? I remember the first few times I taught this as a tutor, having a hard time explaining to other people why this would be the case. And this is the nicest explanation that I've been able to come up with. And so I hope that it is at least satisfactory for you. The textbook explains this the same way, more or less. They use slightly different verbiage, which I find less satisfying, but it's a matter of taste. So I invite you to read the textbook's explanation. It's on page 131. But it's essentially the same thing. They don't discuss what the signum function is. They just say that x over the absolute value of x is -1 because x is negative. And that's really the same thing we're saying. Yeah, well, we definitely follow the textbook, right? So the sections, the question in chat was, are there notes we can follow along with? So I'm working from Stewart's Calculus, 8th edition, Early Transcendentals. It's the same textbook that you have access to as an ebook in WebAssign. And if you would like an electronic copy that you can follow along with, like on your computer, I don't use just their examples, but I do often use their examples, I would be happy to share with you this PDF on the one condition that you don't tell anybody important that I gave it to you. So yes, there is, in a sense, notes, right? So right here, here's what we're doing. So I can show you the textbook explanation if you want to see it. It's right here. This guy, whoa, shit. This guy. So you see here they say in computing this limit, they divide top and bottom by the square root of x squared. And downstairs here, they say that square root of x squared is the absolute value of x is -x because we're sending x to -infinity. So in computing the limit as x goes to -infinity, we must remember that x is less than 0. So the square root of x squared is the absolute value of x, which is -x. We divide the numerator by x. For x equals 0, we get this. So they kind of hack their way through it. They don't show you the algebra steps as carefully as I do, but they get to the same place. That the limit you're computing is the limit of negative square root of 2 plus 1 over x squared. So compare that with what we have here. Negative square root of 2 plus 1 over x squared. In either case, the place we end up, we don't need our limit anymore. As x goes to infinity, the only thing that isn't constant now is 1 over x squared. What does 1 over x squared do as x goes to infinity?
0.
Yeah, he goes to 0. That was one of our theorems from last time, remember? 1 over x to the r for any positive number r has limit 0 at plus or minus infinity. So we end up with the square root of 2 plus 0, all divided by -1, which is negative square root of 2.
Question.
Yeah, go ahead.
Oh, never mind. I wrote the negative inside the square root. I just realized it's on the outside.
I see. It is, yeah. So the square root is just of the numerator, and the downstairs is -1.
But just out of curiosity, what happens if the negative was inside the square root?
Then we would be getting some non-real complex numbers out of this thing, which would indicate a problem. So in this class, I know in algebra and pre-calculus classes, sometimes we do talk a little bit about complex numbers. There will be some moments in Calc 2 where you talk about complex numbers, and there will be some moments in differential equations where you talk about complex numbers. But the rest of the calculus sequence, Calc 1, 2, 3, and differential equations, we deal only with real numbers. So if you end up with a quantity under a square root and the whole quantity is negative, that means something went awry. Something has gone wrong.
Thank you.
Yeah, of course. Of course.
Professor, I have one question. So I'm just looking at it, and I think I looked back in my notes and I forgot to put it, but 1 over x squared, if we're going to infinity or negative infinity, it's going to equal 0, correct?
Correct. Yeah, the theorem that I'm citing there, I'll write it back down in case you didn't get it in your notes. It is an important one. If r is any positive real number, then the limit as x goes to infinity of 1 over x to the r is 0, and the limit as x goes to negative infinity, 1 over x to the r is 0. Yep. To talk about the limit at negative infinity, we do need to make sure that r isn't like 1/2 or some number that would make this function not defined for negative numbers, right? Like the square root of x. I can't talk about the limit as x goes to negative infinity of the square root of x for precisely the reason that Aubrey just mentioned, that we would have negatives under a square root. But as long as r is a number such that this function has negatives in its domain, either of these statements or both of these statements is true. Yeah. So that's the theorem we're leaning on there. In other words, reciprocals of powers of x go to 0. And that's because as x goes to plus or minus infinity, this denominator, 1 over x to the r, the x to the r part, is going to get really big. And the reciprocal of a really, really big number is a really, really small number. And what we mean by really, really small is in the limit is 0. Okay, how are we feeling about this problem? First, technical stuff, algebra questions. Questions, how did we go from here to here, that sort of thing. Any questions like that? Try to fit it all in here.
I have a question.
Yes, ma'am.
So when we were solving the past problems, we would divide both sides by the x term that had the highest power, right?
Yep.
I guess my real question would be why 1 over x squared instead of just dividing it by x squared on both top and bottom?
Because the x squared, where he shows up here, shows up under a square root. So you can think of it like saying the dominant term is the square root of x squared. So I divide top and bottom by the square root of x squared. Does that make sense? In other words, if the square root was not here in the numerator, if as a totally separate problem, we wanted to find the limit as x goes to negative infinity of this function without the square root, I would divide top and bottom by x squared. But since upstairs the x squared is trapped under a square root, I'm dividing top and bottom by the square root of x squared.
Okay, so the idea is to get it out of the square root?
Kind of the idea is to manage the square root. Yeah, the square root is what makes this challenging. That's the idea. So I would like to somehow manipulate the expression algebraically so that the stuff under the square root has a limit I can calculate using the rules I know so far. Right now, as it's given, this top term, as x goes to infinity or negative infinity, this top term is going to infinity, right? It's hard to tell what the total ratio is going to do because this term just grows without bound. He just gets bigger and bigger and bigger and bigger. So I would like to divide out by that term. And that's what we're doing here. And that gets us to a place where I have a constant plus something that's going to 0 under the square root. This is something now that I can manage. Is that a satisfactory answer? If not, that's okay. You can tell me. We can talk about it more.
I'm noticing a mechanical pattern here. It's not feeling very natural. I'd have to say maybe with more practice, it would start to feel a little bit more understandable.
Practice will help, definitely. So, okay, let's do it like this then. Let's do one more kind of a practice problem of this type before I move on to the next type of problem. That's okay.
Yes, that is a beautiful idea. Thank you.
All right. So let's find the horizontal asymptotes . Let's find all of them. Let's find the HAs and the VAs. All right, so horizontal asymptote and vertical asymptotes for f of x equals, we'll keep it real similar, square root of 2x squared plus 1 divided by 3x plus 5. do see there's a comment in chat. I'll take a look at that before we dig in. Yeah, more practice. Okay. There are lots of notes online we can look at. Yeah, if you look at the modules section in Canvas, you'll see lots of links to Paul's online math notes. Those are excellent written resources. And you'll also see lots of links to Patrick JMT videos. I did also add some stuff on piecewise functions. There was a She Loves Math page that was really good on those. So I encourage you to take a look at the modules section for some added practice, resource, examples, those sort of things. So to find horizontal asymptotes, I need to take the limit as x goes to plus infinity of f of x. And I'll also need to take the limit as x goes to negative infinity of f of x. And to find vertical asymptotes, I need to see what makes the bottom equal to 0. I think finding the vertical asymptotes is a little bit easier, so let's do that first. The bottom here is equal to 0 if and only if 3x plus 5 is equal to 0, which is true if and only if x is equal to negative 5/3. So the vertical asymptote is the vertical line, x equals negative 5/3. So with that out of the way, we can find our HAs. First, we'll take the limit as x goes to positive infinity. And since this is very similar to the other function, you can guess that the trick will be a very similar trick. Again, I need to identify the dominant term. Downstairs, I have a linear function. That is a function where the largest power of x is the power 1, right? 3x plus 5. And upstairs, I have a quadratic function, but it's under a square root. And the square root kind of undoes the quadraticness. So both the top and the bottom grow at the speed of a linear function. But the numerator is not actually linear because I can't distribute the square root. Again, the challenge is if I try to plug in infinity for x, then the top looks like infinity and the bottom looks like infinity. I don't really learn anything. That's actually, we'll discover this later, another indeterminate form, infinity over infinity, just like 0 over 0. So in order to figure out what this limit is, I need to do some algebraic manipulation. And again, the trick is going to be to divide top and bottom by the dominant term. The dominant term, I can think of it as x, or I can think of it as 1 over the square root of x squared. Or I can think of it as the square root of x squared. So if this feels safer to you, you can always just do this, right? You can always treat it the way we treated the limit at negative infinity. Upstairs, the square root is necessary in order to merge, in order to get my term to interact with the existing square root stuff upstairs. So upstairs, I needed that square root. Downstairs, we could take it or leave it. Downstairs here, the 1 over square root of x squared, I can just treat that as 1 over x. But if I'm being very, very, very careful, which maybe I should, because we're still kind of trying to get used to this, I'll write it as exactly what it is. It's 1 over the absolute value of x. Now upstairs, I'll distribute the 1 over x squared term. Underneath my square root, I'll do the distribution. 2x squared times 1 over x squared is 2. 1 times 1 over x squared is 1 over x squared. And now downstairs here, I'll have 3x over the absolute value of x plus 5 over the absolute value of x. All right, and we might want to put him in some parentheses to make clear that that's the whole denominator. And it's at this stage where I'm going to make an observation about the sign of x. Since we're sending x to positive infinity, the x's we're considering here are greater than 0. So the absolute value of x is just x. Which means the 3x over the absolute value of x term is really 3x over x. And you can cancel the x's and you just get 3. And the 5 over the absolute value of x term is really 5 over x. Again, just because the absolute value of x is the same as x, because we're considering x's which are positive. So this is the limit as x goes to plus infinity, square root of 2 plus 1 over x squared divided by 3 plus 5 over x. Now let's look at that denominator. 3, this is a constant. He's not going to change as x goes to infinity. What about 5 over x? What does that do?
It gives 0, so I think the limit is going to give us 2/3.
Almost. So the 5 over x term will go to 0, that's correct. And the 1 over x squared will go to 0. But upstairs there's a square root. So it's going to be the square root of 2 plus 0 divided by plus 0. Rather than 2, it'll be the square root of 2 over 3. Okay, so this is the same problem that we did last time, essentially. Only different is that I'm treating the absolute value of x term with the carefulness that it really deserves. It didn't end up making an impact here because I'm sending x to plus infinity, but I'm hoping that doing it this way for the plus infinity limit will help you see why we do it this way for the minus infinity limit. So compare this also to the last problem from Wednesday. You'll see that writing it all out like this takes a little bit more space and is maybe a little bit confusing at first, but it will help you understand why we need to treat the limit at negative infinity the careful way we do. So let's go ahead and conclude what we can from this. Therefore, one of the horizontal asymptotes is y equals square root of 2 over 3. And we still have another computation to do. I still have to do the limit at minus infinity to see if there's a different horizontal asymptote on that side. Remember, like arctangent has a different horizontal asymptote on the left and on the right. So let's go ahead and do the limit at negative infinity. I'm going to use the same trick. I'm going to divide top and bottom by the square by the square root of x squared. Upstairs, I merge the two square roots. And I distribute the 1 over x squared term to get this. Downstairs, I write 1 over the square root of 1 over x squared as 1 over the absolute value of x. And then I'll distribute it. And we'll get this. Here, since we're sending x to negative infinity, the x's are less than 0. So the absolute value of x is equal to negative x. So this becomes lim x to negative infinity, square root of 2 plus 1 over x squared, all divided by 3x over negative x plus 5 over negative x. And now we can cancel downstairs. And what do we get? So upstairs here I'll have 2 plus 1 over x squared. Downstairs here, 3x over negative x, that's negative 3. And this is going to be minus 5 over x. And then the same limit laws, the same theorem that we applied last time, guarantees 1 over x squared and 5 over x go to 0. So this will be the square root of 2 plus 0 over negative 3 minus 0. So out of this, we get the square root of 2 divided by negative 3. Therefore, or thus, the other horizontal asymptote is the line y equals square root of 2 over negative 3. Calculating these specific limits, the limits at negative infinity, where you have to deal with a square root of x squared as the absolute value of x, constitute the more challenging problems from chapter 2. And they're very common Calc 1 problems. So the good news is, if you Google around, you can probably find 15 or 20 different ways to think about it, 15 or 20 different ways to write out the details. The important thing, because this is a skill building class, is that you learn some way to do it that makes sense to you and leads you to the correct answer. And what I'm showing you here is correct, and it is rigorous, and it will always work. And so that's why I choose to show it to you this way, with this level of detail. But I invite you to play around. Read the textbook, by all means. We should always be reading the textbook. Also, look at the things I've posted on the modules in Canvas, watch those videos, see if you prefer one of the other ways of thinking about it. And then finally, if you want to, you're welcome to Google and find other ways still. But make sure you find some way to solve these problems that is satisfying to you and that you understand. Coming by the office hour to work through some of these together and talk through a method would be a really, really wise idea if these feel a little wonky for you. I would like to take a look at the graph of this function that we're playing with. So there you see that. And if I zoom out, you see there really are two different horizontal asymptotes. On the right-hand side, we're approaching some positive number as we sneak out here, and we know what that is. This guy. And on the left side, we're approaching a different number. That's this guy. All right, so as we go further and further out in the negative direction, the red graph is getting closer and closer to the green line. And as we go further and further in the positive direction, the red graph is getting closer and closer to the blue line. So just like the arctangent function, this function has two different horizontal asymptotes, and it also has a vertical asymptote right here where we said it did. All right, so these are all the asymptote information for this function. All right, so one last time, I want to look through this stuff and ask for questions. This time, rather than asking for technical questions, I want to talk about strategic questions. Any questions about what it is we had to do and how we knew what to do? How we knew to set the bottom to 0 to find VAs, or to calculate these limits to find HAs. Do we see the connections there? So remember, you can take the definition of a horizontal asymptote to be the limits at plus and minus infinity. And just like for a rational function, even though this function is not rational because that numerator is not a polynomial, the square root kills the polynomialness, the rule for finding vertical asymptotes still works fine. It's an algebraic function, so you're going to set the bottom equal to 0. Setting the bottom equal to 0 gave me the equation of this vertical line for my vertical asymptote, and then the two limits at plus and minus infinity gave me my two horizontal asymptotes. I calculated the limit at plus infinity here using the same technique that I would use for the limit at minus infinity to help you see that they're really the same thing. This very careful treatment, treating the square root of x squared as the absolute value of x, is never wrong. It's just maybe unnecessary when you're going to plus infinity because the x's you're considering there are positive, so the absolute value of x is the same as x itself. However, when we send x to negative infinity, we need that careful treatment because here the absolute value of x is not the same as x. So what's really at the crux of this is the piecewise definition of absolute value. So at the heart of these technical steps is the definition of the absolute value function. And maybe you haven't seen this. The absolute value function is defined to be x if x is greater than or equal to 0, and negative x if x is less than 0. That's really what's going on here. What does the absolute value function do? Well, in our minds, we say it just makes everything positive. But algebraically, how do you say that? Well, if you're already positive, I leave you alone. And if you're not positive, if you're negative, I slap on another negative to make you positive. So that's really what's going on here. Because I'm sending x to negative infinity, the x's are less than 0, which means the absolute value of x is negative x. So after playing around with my algebra, dividing top and bottom by the square root of x squared, I have my absolute value terms down here, which I can replace by the negative of x, because my x's are negative. So I will double check after class today and make sure that I have plenty of extra practice problems and videos for you to watch in the modules section of Canvas. I do believe there's a fair amount there already, but I'll take a look and make sure that there's a sufficiently large collection for you to play with. And then I also invite you to come by the office hour today from 1 to 2 p.m. if you want to talk more about this particular style of limit problem. Okay, one or two more little things here. We've seen multiply by the conjugate tricks, but we haven't seen them in this context. I'd like to do one of those. So let's evaluate the limit as x goes to plus infinity of the square root of x squared plus 1 minus x. If we try to just plug in infinity, then I get infinity squared plus 1 under a square root minus infinity. Infinity squared is infinity. Infinity plus 1 is infinity. The square root of infinity is infinity. So if you try to plug in here, this looks like infinity minus infinity, which is not 0. It's another indeterminate form. So this looks like, if we plug in, which is not 0. Just like 0 over 0 isn't 1, infinity minus infinity is not 0. It's an indeterminate form. It could be anything. And so here we need another algebra trick, right? You may have heard this before. Calc 1, make sure you remembered your algebra. Calc 2, make sure you remembered your Calc 1. There's lots and lots and lots of algebra tricks in this class. But we've seen the algebra trick that's useful here. When you look at something like this, at this point, it should be screaming at you to multiply by the conjugate, right? We've seen lots and lots of limit problems that require that trick. This is just another one of those. So I will multiply top and bottom by the conjugate of that expression in hopes of getting some nice algebraic result out. The conjugate of that expression is the square root of x squared plus 1 plus x. So I multiply top and bottom by that. And this, of course, I'm thinking as being over 1. Now I distribute my top and I distribute my bottom. We've seen how this goes several times. When I FOIL out my tops, I'll have the square root of this times the square root of this, which is just going to be that thing, x squared plus 1. I'll have minus x times that thing. And then plus x times that thing. So those will go away. And then at the end, I'll have minus x squared. Those are my lasts. And downstairs, I just have the square root of x squared plus 1 plus x. All right, that thing times 1 is just that thing. Now here my middle two terms cancel. All right, these two fellows here, they add up to 0. And so then I have x squared plus 1 minus x squared. Well, that's just 1. So my numerator is 1, and my denominator is the square root of x squared plus 1 plus x. Suppose I should come up here and insert the word usually, or always. not usually or not always 0. In this particular case, we are going to get 0 out. So now what happens? If I go to send x to infinity, I'll have 1 over, I'll write this out, it's going to look a little silly, infinity squared plus 1 plus infinity. Now we said it earlier, but I didn't write it down. Infinity squared is infinity. Infinity plus 1 is infinity. So this is like 1 over the square root of infinity plus infinity. The square root of infinity is infinity. Infinity plus infinity is infinity. So this is 1 over infinity, which is 0. Some kind of valuable intuition. One over infinity, you can think of as being 0. The catch is infinity is not really a number, so doing algebra with it is a bit dangerous. But part of the purpose of a calculus class is to wrestle with this idea of infinity and to try to really understand it. What we're really saying here is that 1 over a really huge number is equal to a really small number. So if you have a limit where the bottom is going to infinity and the top is not, then that limit is 0. And that's what we ended up with here. After doing some algebra, we got a function where the bottom is going to infinity, but the top is just 1. So as x gets bigger and bigger and bigger, the bottom is getting bigger and bigger and bigger, but the top is not. So we end up with 1 over a really, really, really huge number, which is a really, really, really small number. And as that really, really, really huge number is allowed to go to infinity, the reciprocal of infinity is safe to think of as 0. How do we feel about this? Thoughts? Questions? The silence worries me a little bit. Tell me a little bit what you're thinking. Anything.
That is interesting. It's very true. 1 over a huge number is a really small number.
And what about this kind of bizarre arithmetic with the infinities? How do we feel about this?
I find that a little strange.
Yeah, definitely strange, but you know, practice, there you go. Practice fixes everything.
That's true. I think the sort of intuition that I found useful, anytime you see the word the infinity symbol, this lemniscate here is what it's called, in your mind you can think of it as just being a shorthand for the words huge number. So if you take a huge number and you square it and then you add 1, you get another huge number. The square root of a huge number is still a huge number. And if you add 2 huge numbers together, you get another huge number. That was helpful for me. And may be helpful for you as you work through the homework. Yeah, Aubrey?
What if it was infinity squared plus a different number of 1? How would you want us to show you before we just jump into infinity?
Yeah, so infinity plus any constant, still infinity. Infinity plus infinity, still infinity.
What
Infinity,
about infinity minus infinity?
still infinity. Infinity minus infinity is trouble.
Got it.
Could be anything, right? That's an indeterminate form. Infinity over infinity, also indeterminate form. Just like 0 over 0.
What about infinity over like 10?
Fair enough. Yeah, infinity over any constant, still infinity. So like half of infinity, still infinity. 1/10 of infinity, still infinity.
Cool.
All right. Any other questions on like operations with this infinity symbol? Certainly infinity times any positive constant would still be infinity. Feels okay? All right, good. This stuff is important now, and it will be even more important when you get to the section in Calc 2 where you talk about sequences and series. It won't be huge for us, but it is worth playing around with a little bit. So I'd like to do one or two more little examples here, but neither of them are as technical or as complicated as the ones we're looking at. So let's go ahead and do that. Look at the limit as x goes to, well, we could say 2 from the right or 2 from the left. We'll do 2 from the right. Of the inverse tangent of 1 over x minus 2. There can be, yep. James in chat asks, what is the absolute value of infinity? The absolute value of infinity, also infinity. If you're interested in that sort of stuff, you can look into what's called the extended real numbers, which is a tool that measure theorists and analysts use. It's a set of numbers like the real numbers, except it also includes the symbol infinity and defines the arithmetic on infinity precisely. That's the extended real numbers. There's a good Wikipedia page, although you might find it a little bit hard to read. But let's come back to this guy. So as x goes to 2 from the right, what does 1 over x minus 2 do? In other words, let's forget about the inverse tangent for a minute. What is the limit? Let's see just what the inside does.
It's undefined.
It's true that if you plug 2 in, it's undefined. But what does the graph of 1 over x minus 2 look like? He has a vertical asymptote here at 2. And aside from that, he looks just like 1 over x. He's just been shifted to the right by 2 units. All right, you guys remember your transformations of graphs from pre-calc? So this is the graph y equals 1 over x minus 2. Oh shit, no, actually, I'm sorry, I drew this backwards. Sorry. 1, 2, vertical asymptote. Yeah, it's the graph of 1 over x shifted to the right by 2 units. So I'm getting that from the transformations of graph stuff that you cover in pre-calculus. Taking the graph of 1 over x and shifting it to the right by 2 units. So this is 1 and this is 2. So as x approaches 2 from the right, 1 over x minus 2 goes to plus infinity. So we could say observe or recall. The limit as x goes to 2 from the right, 1 over x minus 2 is plus infinity. Therefore, the limit as x goes to 2 from the right of the inverse tangent of 1 over x minus 2. There's kind of two ways to say this. You could either say that it's equal to the inverse tangent of plus infinity, which is pi over 2. Or you could say that the limit as x goes to 2 from the right of the inverse tangent of 1 over x minus 2 is equal to the limit as x goes to infinity of the inverse tangent of x, which is still pi over 2. I'm partial to this approach. So in other words, we ask, what does the inside do? The inside is going to plus infinity. And then we say, okay, well, what does the inverse tangent do as its inside goes to plus infinity? Well, he has a horizontal asymptote on the right side of pi over 2. So as his inside goes to plus infinity, inverse tangent goes to pi over 2. Therefore, the inverse tangent of plus infinity is pi over 2. This down here maybe feels a little bit more rigorous, but I don't think it's fair to say that. I think either of these are fine. Well, you have to remember what arctan does. So this was one of the examples that we did back on Wednesday, right? So arctan on his own, got to remember all these graphs. Looks like this. So I don't care about this guy right now, but as the inside of the inverse tangent function goes to plus infinity, the function arctan goes to pi over 2. So in other words, this down here, this was something that we showed from the graph on Wednesday. So that's what we're leaning on here. Sometimes when we do this little thing here, we make a substitution. So if you prefer, you could say let u equal 1 over x minus 2, and then rewrite this as the limit as u goes to infinity tan inverse of u, and then say, okay, well that's pi over 2. There's a bunch of different ways of writing this sort of thing, but really I think the top notation there, the boxed notation, is the most convenient, simplest way to do it. It's the way that I see most students do it that feel like they have a firm understanding of the stuff. Okay, how do we feel about this? Look at the boxed work here. This is definitely the cleanest way to think about it. I want the limit as x goes to 2 from the right of the inverse tangent of 1 over x minus 2. I know that 1 over x minus 2 goes to plus infinity as x goes to 2 from the right. So the limit as x goes to 2 from the right of the inverse tangent of 1 over x minus 2 is the same as the inverse tangent of plus infinity, because the inside of that function is going to plus infinity. And then the inverse tangent of plus infinity is pi over 2, because the horizontal asymptote on the right-hand side for the inverse tangent function is pi over 2. Are we able to follow that logic?
Yes.
Okay. So this is the type of argument you want to get comfy making. There are different ways of writing it. Your textbook does use this substitution thing. So they say that the limit as x goes to 2 plus of arctan 1 over x minus 2 is equal to the limit as u goes to infinity of inverse tangent of u, which is pi over 2. There's even a third way of writing this, but I don't want to give you too much alphabet soup. I really do believe, having done this for many years, that getting comfy with the arithmetic of infinities is the way to go. So here you can just think about the limit of the inside. The inside goes to infinity. What's arctan of infinity? Oh, it's pi over 2. That's one of those limits we know. I do have another limit that I want you to know in the same sort of way. And this is something that you've really known since college algebra. It has to do with exponential functions. I want to look at this and this. Both of these, just like the arctan limit, are going to come from the graph. Here's the graph of e to the x. This is the point 0, 1. Over here we have the point 1, e, and so on. He does have a horizontal asymptote over here. You guys remember that from your algebra classes, I'm sure. But he only approaches it on the left. So by the graph, the limit as x approaches positive infinity of e to the x, if I wander off to the right along this graph, he just gets huge. That's plus infinity. And the limit as x goes to negative infinity of e to the x, if I wander off on the left side of the graph here, I get closer and closer and closer to 0. It's that second limit that's especially important. And we can use that to calculate some different limits. So this, think of this as being like the arctan limit, right? As x goes to negative infinity, arctan goes to negative pi over 2. As x goes to plus infinity, arctan goes to positive pi over 2. Those are two limits that you just need to know. We know them from the graph because the arctan function is a function we know well. Same thing here, right? E to the x is a function that we know well. Its graph is one that we have memorized, so we can get these limits straight from the graph, and they're important limits. They're limits that we need to remember. A nice example homework style problem that you can get out of this is the limit as x goes to 0, let's say from the left of e to the 1 over x. This is similar to the last problem we did, where I'm going to think about what happens on the inside. So my inside function here is 1 over x. As x goes to 0 from the left, what does 1 over x do?
One over s is undefined.
That's true. It is undefined at 0. But as we approach 0 from the left, what does it tend towards?
Infinity towards the left.
Almost. That might be one way to say this. Let's look at the graph. So here's the graph of 1 over x. So as x goes to 0 from the left, we're diving down here, right? And we have this vertical asymptote. So as x goes to 0 from the left, 1 over x goes to negative infinity. So what is this limit really? It's e to the negative infinity. But what is e to the negative infinity? Well, according to this thing we just did, the limit as x goes to negative infinity of e to the x is 0. This is the same as saying e to the negative infinity is 0. So this is 0.
Is it because we're trying to understand that it's approaching 0?
Right. Yeah, that's the idea. As x approaches 0 from the left, e to the 1 over x approaches 0.
Okay, thanks.
If you wanted to do this in the substitution notation, we could say that the limit as x goes to 0 from the left of e to the 1 over x is the same as the limit as u goes to negative infinity, e to the u. And then by the work we did above, the limit as its variable goes to negative infinity, e to that variable, that's 0. Either approach is fine. Again, I prefer the top approach. Some might say that it feels a little bit sloppy, but I would disagree. I think that this approach, just like the boxed approach to the previous problem, is the fastest and cleanest way to get at what we're trying to get at. The textbook does this substitution gimmick, which is okay. There's nothing wrong with it. It works well. But I don't feel like it gives you any extra insight, and it doesn't get you to the answer any faster. And it's not using anything that we're not using in the boxed approach. So in both this and the last example with the arctan, we had to think about what the inside function did. And then to figure out the overall limit, we ask, okay, well, what does the outside function do as the inside function does what it does? So here the inside function is 1 over x. And as x goes to 0 from the left, 1 over x goes to negative infinity. So the limit as x goes to 0 from the left of e to the 1 over x is like e to the negative infinity, because 1 over x goes to negative infinity. And according to this limit, e to the negative infinity is 0. Yeah, Krishna, stick around at the end of class. We'll talk about that. Okay. Other questions or comments on this limit? Okay, so I think that's just about time for the class today. I want to really, really briefly introduce you to what we're going to be talking about next. So over the weekend, make sure you finish up the 2.6 homework. The homework load for this week is fairly light. It is due on Monday, and if you need a little bit more time, I would be happy to extend those for you, but I want everybody to stay on pace. So please try to get everything done by Monday, by our class on Monday. On Monday, we're going to start talking about the derivative, which means we're going to need to talk a little bit about slopes. We know that straight lines have a single slope, but most functions are not straight lines. Most functions have graphs that are curvy like this. But what I would like to do is have some idea of what is the slope of the function right here at this point. And you can see I can kind of draw in a line that passes through that point that appears to have the correct slope. So how do I get at how do I find the slope of a function which is nonlinear at a point? You may remember this idea of an average rate of change being the slope of the secant line that connects 2 points on the graph. That's this guy. The slope of that first dotted line is the average rate of change for f from A to B. The slope of this guy right here would be the instantaneous rate of change. And that's the thing I want. And it turns out to connect the two, we take a limit. We're going to take this guy and send this number over here to this number. As I let B get closer and closer and closer and closer to A, the slope of this secant line will look more and more like the slope of this tangent line. And that's really the main object of study in Calc 1, tangent lines, slopes at a point. So I'm going to show you several ways to write expressions like this, which you may remember are called difference quotients. And then we're going to take limits of those difference quotients using all the tricks that we've been learning the last 3 weeks in order to get out the slope of that tangent line, which is called the instantaneous rate of change. It turns out that this is a beautiful tool for finding minima and maxima of functions, right? The tops of hills and the bottoms of valleys. It's also a really good tool for finding when a function is increasing and when a function is decreasing. And so that is where we're going. All of this limit stuff that we've been doing is just assembling tools in order to take specific limits of these things so that we can talk about slopes for functions where the slope changes, right? Because this function definitely doesn't have a constant slope like a linear function would. But there is a way to find a formula for the slope at any given point. In fact, we'll be able to find a function whose output at any given point is the slope of the original at that same point. So that's where we're going to be going. As long as you are done with all of the homework that we've put out so far by class on Monday, you'll be in great shape to get there. So if any of that is hanging you up or giving you a hard time, please come by my office hours, send me emails, whatever it is. If you can't make my regular office hours, send me a Canvas message saying, hey, could we meet at this time on this day? And I'll either be like, yeah, or nah, can we do it at this time instead? But I promise you, I don't have a problem doing that, happy to do it. And I really want to make sure everybody is up to speed by Monday so we can really dig in, because this is the start of Calc 1 in earnest. Limits are important, but they're really just tools that allow us to get at this new concept of the derivative. So yeah, that's where I will leave it for today. If you have any questions, don't hesitate to Canvas message, email, or come by office hours. And I hope you guys have a lovely weekend. Is there any last minute stuff we want to talk about? I know Krishna had a question about WebAssign. Using the React tool, how many have been kicked out of WebAssign, cannot currently get into WebAssign due to the trial access ending? It's okay, don't be ashamed. Happened to me. Okay, and I know at least 2 other people have talked to me about this. So Diana, if anybody else, Audrey, send me messages on Canvas, all right? And the same goes for you, Krishna, while we're here. Anybody who has been kicked out of WebAssign because their trial access ended, send me a message on Canvas immediately. I've already contacted our Cengage rep for one person in that situation, and she was happy to extend the trial access for a few more days until that person was able to afford an access code. I don't want anybody missing out on class or unable to do homework because you can't get in there. So if that applies to any of y'all, I see a handful of people replying in chat. Each of you, please send me your own Canvas message, and then I will forward that information off to our Cengage rep and try to get you back in as quickly as possible. It's not something I can do myself. It's something I need to hand off to somebody else. So in order to get you in there quick, we got to do it like now. That way you'll be able to continue working over the weekend. Yeah, no, if you already paid, that's awesome. The people who I am going to try and extend this for will still have to pay. It's just that you'll have a few more days before you have to pay, so you can continue working the homework. All right, I know payday for everybody, myself included, is like tomorrow or the day after. So I want you guys to be able to work on this stuff, even if you don't have the money to buy it right now. Okay, so if that's you, if you got booted out, send me a Canvas message. Any other last minute questions before we end the meeting or anything that we're concerned about? Okay, all right, so if you need that extended, send me the message, I'll do it, or I'll send it off to the Cengage people who will hopefully do it right away. Otherwise, have a lovely weekend.